So far we have studied nodal analysis, which is a systematic way of setting down the equations for the circuit and using matrix inversion to solve for the node voltage variables in the circuit. Now the limitation is that whatever we have studied so far applies to circuits with independent current sources and resistors. Of course, we can have other components in the circuit such as independent voltage sources and also control sources. So what we are going to do now is to adapt nodal analysis for use in those cases. The case of circuits with resistors and only independent current sources is the easiest for nodal analysis, but it can be used for others with a little bit of tweak. Okay. So let's take this circuit which has a voltage source. Looks very similar to the circuit we used earlier, except that one of the resistors is replaced by a voltage source. Okay. Now what is it that we did when we carried out nodal analysis? We took every node. As usual, I'll define this to be the reference node, and these node voltages are V1, V2 and V3. Okay. Now we looked at every node, and at that node we wrote KCL equations showing the currents flowing out of that node being equal to the independent current being injected into that node. Okay. Now what is the problem when we have a voltage source? Clearly we have to write I11 plus I12 to be equal to the current being pushed here, which is I1. Okay. The problem here is that we cannot relate this I12, the current through the voltage source, to the voltage of the voltage source. Now if we have a resistor, and let's say I have V1 and V2 on either end of the resistor, so the voltage across the resistor is V1 minus V2. Now this is enough to tell me what the current is by Ohm's law. That current will be V1 minus V2 divided by R, where R is the value of the resistor. Okay. On the other hand, if you have a voltage source with V1 and V2 at either ends, the voltage of the voltage source of course is V1 minus V2. It has to be for these two voltages to be V1 and V2. Now there is no relationship between this current here through the voltage source and the voltage across the voltage source. In fact, the definition of the voltage source is that it maintains a given voltage regardless of what current is flowing through it. So you cannot determine the current through a voltage source from the voltage of the voltage source. Okay. The current in a voltage source is determined by whatever it is connected to, external constraints. Okay. So when I write my equation for node 1, I would write I11 plus I12 equals I1. I11 of course is V1 divided by R11, but I12 I don't know, I cannot express it in terms of voltages and element relationships. So I have to keep I12 as it is. Okay. So this is still a variable, and the same problem occurs with node 2. Basically the voltage source is connected between node 1 and node 2. So again at node 2 I have to write I22 plus I13 minus I12, because I am taking all the currents to be flowing away from the node to be equal to 0. Okay. So I have to write minus I12 plus I22 plus I13 to be equal to 0, because no independent current source is injecting into node 2. Again, I don't know the value of minus I12. I22 and I13 I can relate to the voltages and resistor values. Okay. This is the essential problem when we have voltage sources in a circuit and we have to carry out nodal analysis. The currents in voltage sources cannot be related to the voltage across the voltage sources. Okay. So what is it that we do? So you notice that again the voltage source is connected between node 1 and node 2, and in node 1 this I12 appears with a positive sign, and in node 2 it appears with a negative sign. Okay, it doesn't matter in which direction we take I12. We could have taken this way or leftwards, but in one of the node equations it is getting pushed into the node and it will be subtracted from the left hand side, and for the other node it will be pulled away from the node, it will be flowing away from the node and it will be added to the left hand side. Okay. So clearly we cannot use this I12 in our equations, so we have to eliminate it, and that we can do by combining the equations for nodes 1 and 2. Okay. So let's look at that. So again I will take I12 that way. Okay. And for node 1 I would write V1 times G11 plus I12 equals I1. For node 2 I would write minus I12 plus the current through R22, which is V2 times G22, plus the current through R13, which basically gives you V2 times G13 minus V3 times G13 equals 0. Okay. Now if I sum these two equations, what will I get? This I12 goes away and we will have V1 times G11 plus V2 times G22 plus G23 minus V3 times G13 to be equal to 0. Okay. So we have combined the equations for nodes 1 and 2 into a single equation, and we don't have this problem of the unknown current in the voltage source. Because the unknown current in the voltage source is going from node 1 to node 2, it appears with a plus sign in the equation for node 1, minus sign in the equation for node 2, and gets cancelled out when I add the two equations. Okay. So that's fine. So we have got rid of the unwanted variable. But now the problem is that we have lost one of the equations. Before I had three variables V1, V2 and V3, and I had three equations KCL at nodes 1, 2 and 3. But now I have combined the equations at nodes 1 and 2 into a single equation. So instead of two equations I have only one for both nodes 1 and 2. But I do have the constraint of the voltage source, so that gives me the missing equation. Okay. Meaning I lost one equation because I added KCL equations for nodes 1 and 2. On the other hand, I also know that this V0 will constrain V1 and V2. Okay. That means that V1 minus V2 equals V0. Okay. So this voltage source equation so I have this voltage source equation in place of the missing equations. Okay. So what are my three equations now? I have a combined equation for nodes 1 and 2. Which are those nodes? Those are the nodes between which the voltage source is connected. So I have V1 times G11 plus V2 times G22 plus G23 minus V3 times G13 equals I1. Okay. What are my three equations? For nodes 1 and 2, between which the voltage source is connected, I have a single equation, which is V1 times G11 plus V2 times G22 plus G23 minus V3 times G23 equals I1. Okay. And for node 3, I have the same equation as before. So V3 times G23 plus G33 minus V2 times G23 equals I3. And finally, I have the voltage source equation itself, which is that V1 minus V2 equals V0, the value of the voltage source. So again, I have three equations in three variables. The three variables are V1, V2 and V3, and I can solve for these three variables. Okay.